Welcome to transforming nonlinear equations into separable equations. So the idea here, recall that we used variation of parameters to transform non-homogeneous linear equations into separable equations. And the way we did this was that we did this by setting y equal to u times y1, where y1 was a solution to the corresponding homogeneous equation. So we're going to do something similar here, except the only problem is we don't have a corresponding homogeneous equation. So the question becomes, what do we use for y1? So we will use the same technique, but what do we use for y1? So the first equations we're going to look at are ones that are so close to being linear that we can actually use the usual y1. And then we will generalize from there in the next video. So first up, let's take a look at Bernoulli equations. So Bernoulli equations take a similar format to linear equations. So what we're looking at here are y prime plus p of x times y is equal to g of x times y to the r. So that times y to the r makes this no longer linear, but you can see that the format looks very similar to what we've worked with before. What we will do is we will set y1 to be a solution to the equation y prime plus p of x y equaling 0, what would be the homogeneous equation if we were linear, right? And then now we'll set y equal to u times y1. So then we have the y prime is equal to u prime y1 plus u times y1 prime. So now let's go ahead and plug into the original differential equation. So we'll plug this into y prime plus p of x y is equal to g of x times y to the r. And we get then that we have u prime times y1 plus u y1 prime plus p of x times u y1 is equal to g of x times u y1, the whole thing being raised to the r. Rewriting this a little bit, we have u prime times y1 plus u times y1 prime plus p of x y1 is equal to u to the r times g of x times y1 to the r. Now, this part in the middle, the y1 prime plus p of x y1, this whole thing just goes to 0 by definition of y1. So we are now looking at a separable equation. U prime y1 is equal to u to the r times g of x times y1 to the r. And this therefore becomes u prime over u to the r is equal to g of x times y1 to the r minus 1. From here, we have separated the variables. Again, y1 is a solution in terms of x, and we already know y1 at this point. So we get that the integral of 1 over u to the r dr is equal to the integral of g of x times y1 raised to the r minus 1 dx. We can integrate that left-hand side. And that becomes, so we're looking at u to the negative r, so that would become u to the negative r plus 1, or 1 over u to the r minus 1. And then out front, we would have a negative r plus 1. That's our new exponent on u. And this is equal to the integral of g of x times y1 to the r minus 1 dx plus c. From here, we can go ahead and solve for u if we like, and then we can solve for y, right? So I'm just going to give myself a little more space first. So again, from here, you could solve for u. It will likely involve taking roots and doing some reciprocals, right? And then we get that y is equal to u times whatever your y1 was, right? So this is how we can go about solving a Bernoulli equation. So from here, let's go ahead and look at the Bernoulli equation. Y prime minus 2y is equal to xy cubed. So again, we'll first solve for our y1. And we look at our usual y prime minus 2y equals 0 to solve that. So y prime minus 2y equaling 0. This has solution y1 is equal to e to the integral of 2 dx, or y1 is equal to e to the 2x. Then if we set y equal to u times y1, we are looking at y is equal to u times e to the 2x. We know that we have u prime over u to the r is equal to g of x times y1 to the r minus 1. In our original equation, scrolling back up, our g of x is x and r is 3. So going back here, we have u prime over u cubed is equal to x times y1 to the 3 minus 1, or our u prime over u cubed is equal to x times y1 squared. And of course, our y1 was e to the 2x. So we have y prime over u cubed is equal to x times e to the 2x, that whole thing squared. So u prime over u cubed is equal to x e to the 4x. And then we can go ahead and integrate it. At this point, we have the integral of 1 over u cubed du is equal to the integral of x e to the 4x dx. 1 over u cubed we can integrate fairly easily. That will go to 1 over u squared, but then we'll have to multiply by a -2. So this will be a -2 over u squared. Right, that's u to the -3, raise the power by 1, we would go to u to the -2. And then, oops, sorry, we divide by our new power. This should be -1/2 times 1 over u squared, or just -1 over 2u squared. On the right, we will need to do a little integration by parts. So we'll go ahead and set our u to be x, since that'll go down with the with differentiation. Our dv will be e to the 4x. Differentiating down the left, we'll go to 1 and then 0. Integrating on the right, we'll have 1/4 e to the 4x and 1/16 e to the 4x. We will add the product on the first diagonal, subtract the product on the second diagonal. So we are looking at 1/4 x e to the 4x, and then minus 1/16 e to the 4x. From here, we can go ahead and solve for u. Oh, we should have a plus c as well. So solving for u, we can multiply by a -2. We have 1 over u squared is equal to -1/2 x e to the 4x plus 1/8 e to the 4x. And I'm going to just make this a plus c1. If we take a constant and multiply by 2, we can still hit -2. We can still hit any constant we want. Then we have, I'm going to write this all together. 1 over u squared is equal to, giving a common denominator, we would have a -4x to the, -4x e to the 4x plus e to the 4x plus c2 all over 8. And so we have then that u squared is equal to 8 over -4x e to the 4x plus e to the 4x plus c2. And therefore u is equal to either the positive or negative square root of 8 over -4x e to the 4x plus e to the 4x plus c2. At this point, we go back to the beginning. Our y was equal to u times y1. So y is equal to, our y1 was e to the 2x. And then we are multiplying that by that square root. And we will have a plus or minus out front. So y must take the, or y takes the form plus or minus e to the 2x times the square root of 8 over -4x e to the 4x plus e to the 4x plus c2. It was not the most pleasant of equations, but it does, it was one that we could get to. So again, for Bernoulli equations, where it essentially looks linear, the only thing we have is that we have that times y to the r on the right. We can do more or less what we did before. There's just a little more work than for the solving for u. So this is one example of using variation of parameters to solve or to convert a nonlinear equation to separable equation and then solve.